Thanks again for the opportunity. So our presentation this afternoon is on integrating sustainability and resilience in bridge assessment and design. And we will be presenting 4 case studies demonstrating these concepts on projects that we've recently completed in KwaZulu-Natal. However, before we go into the case studies, I thought it would be best to quickly define the principles of sustainability and resilience, just to give some context to this evening's case studies. So what is sustainability? Sustainability is the ability to maintain a process or system over the long term, which includes meeting present needs without compromising the ability of future generations to meet their own needs. It balances social, economic, and environmental goals, as often depicted by this graphic on the right-hand side. What does this mean for bridges? It means that bridge sustainability is achieved through a combination of design, materials, construction, and long-term management that minimizes environmental impact and ensures structural resilience and longevity. So what is resilience? Resilience means the capacity of social, economic, and environmental systems to withstand or recover from a disturbance, from a hazardous event, in ways that maintain the essential function and identity of the structure. The principles of resilience generally encompass the 4 R's as shown on the right-hand side here, which entail robustness, redundancy, resourcefulness, and rapidity. Resilience and sustainability are, of course, closely linked. Resilience supports sustainability by ensuring the longevity of a system and its ability to recover from a disruptive event. The principle of resilience, as I said, encompasses these 4 principles as given by Brunet et al. 2003. So why are these concepts important, and especially for bridge design? So a sustainable and resilient bridge design leads to, of course, a reduced environmental impact, reduced overall costs, and improved social and safety benefits. These principles will be demonstrated in the case studies that we will be presenting by my colleagues later this afternoon. And the case studies that we will be presenting, Adrian will kick us off with the design and construction of the Canelands Pipe and Pedestrian Bridge. I will follow him with the rehabilitation of the flood-damaged Mshlali River Bridge. Tabikile will then speak on the fire damage assessment and repair of the Sanya Road Bridge, and Abish will end off with the emergency rehabilitation of the Mzimkhulu River Bridge. So that's it for the introduction. So now I'll just hand over to Adrian, who can take us through the first case study. Thanks. Adrian, please just unmute.
Good evening, all. Apologies. This evening I'll be through the design and construction of the Canelands Pipe and Pedestrian Bridge. Just give me a minute to upload the presentation. This is a brief outline of the presentation that we will embark on now. Introduction, a brief introduction. The newly constructed Canelands Pipe and Pedestrian Bridge is a 165-meter long post-tensioned concrete structure that spans the Mdloti River in the Canelands area of Verulam, KwaZulu-Natal, within wards 58 and 60. This project involved dismantling the century-old South African railway structural steel bridge, which was at an advanced stage of deterioration, and replacing it with a modern post-tensioned pipe and pedestrian bridge, as earlier studies indicated that rehabilitation of the existing structure would not be cost-effective. The bridge was originally designed and used as a railway bridge in its early years, but was later repurposed by eThekwini municipality to carry a 400mm sewer pipe, a 350 and 400mm water pipe, as well as electrical and fiber optic cables across the Mdloti River in a north to south direction over the bridge deck. Infrastructure reuse and resource optimization. Itiquini municipality put out a tender to design a new pedestrian bridge alongside the old steel truss railway bridge and thereafter demolish the old steel truss railway bridge. One of the critical criteria was that all existing services that the bridge carried, like sewer, water, and fiber main pipelines, had to remain operational during construction. Nile Consulting submitted an alternative tender whereby it was proposed to utilize the existing rail bridge substructure, thereby saving the client approximately 20 million rand in construction costs. The phrase constructing a bridge within a bridge aptly captures the innovative construction methodology employed. The new post-tension bridge deck was built within the envelope of the deteriorated steel superstructure. This approach posed significant challenges, yet offered distinct benefits, chiefly the avoidance of temporary works within the river channel, thereby minimizing environmental disruption. Crucially, pedestrian movement and essential services remain uninterrupted throughout construction. Despite the deterioration of the original bridge, Nida Consulting engineered a solution that ensured safe passage and service continuity. The structure comprised of a continuous composite post-tension beam and reinforced concrete slab deck, consisting of adapted U-beams and a 350 millimeter thick reinforced concrete top slab. The continuous U-beams encases the gravity sewer line, comprising a structured wall HDPE pipe. The selection of the HDPE pipe was based on its reduced weight, which was vital in reducing the load on the existing bridge structure. The HDP is also inherently flexible and can withstand larger deformations and deflections than that of rigid and brittle pipe materials. In using the post-tension beam, which was cast within the existing steel truss option for the bridge deck, staging for the bridge deck over the river floodplain was completely eliminated in addition to the ease and speed of construction. The deck slab was made continuous over the piers to eliminate the necessity for expansion joints, limiting them to the buttons only. A notable aspect of this project was the procurement phase, which occurred during COVID-19 pandemic period. In response, Nidec Consulting leveraged advanced 3D design software, drone imagery of the site, and building information modeling technologies to provide the first ever virtual briefing in eThekwini municipality. The original design proposed precast, pre-stressed U-beams with an in-situ concrete decks launched onto retrofitted supports. However, upon site establishment, the contractor identified opportunities for improved efficiency. A proposal was submitted to cast the deck in situ using custom formwork, which was suspended off the existing steel trusses due to limitations in the condition of the existing structure and logistical constraints. This did not require specialized launching equipment, neither did it require scaffolding from the riverbed, thus ensuring no environmental items were triggered. NIDA Consulting rigorously evaluated the revised proposal and approved it, as it adhered to the original intent with minor geometric modifications. This collaborative design-build approach embodied value engineering, delivering cost savings without compromising structural integrity and the original design intent. This adaptation exemplified effective value engineering, resulting in notable cost savings for the client. A critical geotechnical intervention, if you notice on the top left of your screen, was necessitated due to the pre-construction failure of the northwest abutment ear wall, caused by severe flooding. This was addressed through the construction of a 12-meter high gabion retaining wall. This not only prevented further scour and structural compromise, but also created employment opportunities and skill development for local laborers through a labor-intensive construction method, aligning with community upliftment objectives. Environmental sensitivity, aesthetic integration, and biodiversity enhancements. To honor the legacy of the old structure, the design of the new bridge incorporated balustrading that closely mirrors the steel truss superstructure of its predecessor, offering a tribute to the original design, emphasizing the commitment to heritage preservation. Similarly, the choice of colors for the balustrading was closely selected for integration onto the natural surrounding environment. By retaining and reutilizing the existing substructure avoided environmental triggers, as working within the watercourse was now not necessary. thereby negating the need for formal environmental authorization or a water use license. The planter boxes were incorporated into the retrofitted pier extensions, enhancing both environmental value and visual harmony with the surrounding landscape, contributing to the ecological value and urban greening effects.
Ngizama uku-attend i-meeting la kungeneki.
Energy efficiency and low maintenance designs. Given the high costs of electrical lighting, load shedding, and the issue of theft, an innovative solution was proposed to illuminate the bridge by means of glow-in-the-dark concrete in the architectural balustrades. This feature enhances safety by enabling the balustrades to glow in the dark, improving visibility for pedestrians at night while reducing the need for electrical lighting. Moreover, the technology minimizes maintenance requirements and mitigates the risk of vandalism, delivering both practical and long-term benefits for the community. The technology utilizes the use of phosphorescent particles that, when combined with the polymer concrete, will cause the concrete to glow in the dark. The particles have the ability to absorb natural light during the day and to release the stored energy at night in the form of visible light. This provides a guiding light for up to 12 hours. It has proven to be a very successful venture in providing the much-needed light to the communities. Careful selection in the types of materials and the construction approach chosen for construction, which ensured it was durable and vandal-resistant for long-term performance with a minimal upkeep. For example, the selection of HDPE pipes encased in concrete requires little to no maintenance and little to no monetary value for theft. The deck piers were made continuous, eliminating the necessity for expansion joints and the maintenance thereof. Environmental impact statistics. Two notable aspects to this on this project, one being the concrete carbon dioxide equivalent emissions. The typical factor for ordinary Portland cement concrete ranges between 150 to 300 kgs of carbon dioxide equivalent per cubic meter. By reutilizing the existing substructure and adopting gabion basket retention measures, approximately 1,000 cubic meters of concrete was averted on this project. Hence, by assuming an average of 240 kgs of carbon dioxide equivalent emissions per cube equates to 240,000 kgs or 240 tons of carbon dioxide equivalents avoided. To put this into perspective, is equivalent to driving a petrol vehicle for 1 million kilometers, powering 30 homes with electricity for a year, 4,000 trees growing and absorbing CO2 for 10 years, and 180 one-way flights from South Africa to Dubai. The benefits of the reduction in creation of concrete cuts the CO2 emissions, preserves natural resources, promotes circular design, and moves the project towards net zero goals. The second aspect was the lighting CO2 equivalent emissions. In opting to utilize the glow-in-the-dark technology, negated the need for conventional electrical lighting. Assuming a requirement of 1 light pole per span was required, that being 5 light poles in totality, and the emission thereof, results in the following CO2 equivalent reductions. 5 tons of CO2 equivalents from the material and manufacturing stages, 24 tons of CO2 equivalents in operational energy over a 20 to 25 year span, and 3 tons of CO2 equivalents in maintenance over a 20 to 25 year span. This is comparable to driving 7 petrol vehicles for a year, 9,600 liters of petrol not being burned, powering 4 homes with electricity for a year, and 48 one-way flights from South Africa to Dubai. Resilient infrastructure. In conclusion, by considering and incorporating the following design and construction interventions, amongst others, like the reuse of shutters, the reuse of existing infrastructure, the adoption of glow-in-the-dark technology, the omittance of bridge expansion joints, the choice of retention measures adopted, the design of post-tension superstructure, significantly reduced the reinforcement and concrete requirements, which minimize construction waste and environmental impact, as well as directly contributed to the intentional reduction of the project's carbon footprint and emissions thereof. By combining historical preservation with community-focused design, environmental sensitivity, and technological innovation, Nida Consulting has delivered a bridge that not only addresses contemporary needs, but also honors the past while ensuring a sustainable and efficient future for local community. The project exemplifies how technical ingenuity, environmental responsibility, and community-focused design can converge to deliver infrastructure that is forward-looking and respectful of the past, resulting in the final structure being robust, low maintenance, and built to withstand future demands with minimal maintenance. A notable achievement of the project is its receipt of the prestigious SAICE Award for Technical Excellence in 2025. I hope this has invoked a sense of intention within us, and thank you for hearing me out.
Thank you, Adrian, for that presentation. I'll move on then to my presentation, which is a case study on the rehabilitation of the Mhlali River Bridge that was damaged by catastrophic flooding in KZN in April 2022. So the rehabilitation of the Mhlali River Bridge also included adaptation for improved resilience for future extreme weather events. I'm sure most of us remember the April 2022 flood, so this may still be very fresh in your minds. Let me just give me a second to share my screen. Okay, you should all be able to see that. My presentation this afternoon will encompass the following. I'll start off by looking at the rainfall and flood event that caused the damage to the bridge. We then analyze the magnitude of the flood event and calculate the hydrodynamic and hydrostatic forces that caused the damage. I will then describe the rehabilitation measures undertaken to restore the bridge, including the adaptation measures retrofitted to the bridge for improved or increased resilience for extreme weather events before concluding with the presentation. So starting off with the introduction, just to give some background, the Mhlali River Bridge is located on National Route 2, and this is on the east coast of South Africa. National Route 2 provides an important economic link to the port of Durban from areas north and south of the country and into southern African countries. The bridge is owned and managed by the South African National Roads Agency, SANRAL. So the northbound bridge was damaged by flood action in April 2022 from debris blockage, overtopping, and scour. The bridge superstructure was displaced off its bearings 600 millimeters laterally downstream. Both approaches were scoured out, leaving the approach slabs unsupported. As a result, the bridge was immediately closed to traffic, causing significant disruption to National Route 2. Just some details on the bridge. The northbound bridge was built in the 1960s, and prior to this, it was generally in very good condition. It comprised of 7 simply supported spans, each 17.6 meters long, giving a total length of 123 meters. The superstructure comprised of a pre-stressed precast girder beams with a reinforced concrete deck slab, and this was supported on wall-type piers and full-height abutments, all founded on piles down to rock. Now, looking at the rainfall and flood event that actually caused the damage. So Storm Isa, I'm sure some of you will remember this, started on Saturday, 9th April 2022 and continued for 4 days in the province of KwaZulu-Natal. The cut-off low system brought high rainfall intensities over a long duration, which resulted in saturated ground conditions. This caused widespread flooding and damage to infrastructure in the region. In the 24 hours between 11th and 12th April, where the most severe damage occurred, weather stations in Durban recorded overnight rainfall depths in excess of 300 millimeters. Just to put this in perspective, 300 millimeters is approximately 1/3 of the region's mean annual precipitation received in just a 24-hour period. A study subsequently undertaken by the South African Geographical Journal confirms that this was the most catastrophic natural disaster recorded in KZN since 1850, and this measurement is in terms of the number of lives lost, which was unfortunately 459, in terms of the infrastructure damage, which included 4,000 homes, and in terms of the economic impact, which was estimated to be $2 billion. So just describing the damage that occurred. So in the morning of April 12th, when the bridge was inspected, it was found that the bridge deck was overtopped. All 7 spans shifted laterally as a unit up to 600 millimeters in a downstream direction. The fill on both approaches had scoured out, leaving the approach slabs unsupported, and significant debris was found on the deck and trapped on the pier. So in these pictures in the bottom, you can see the shift in the deck in the downstream direction. You can see that by the displacement of the parapet relative to the approach. You can see it in this picture as well. You can also take note of the significant debris that was caught on the deck. This picture is another view along the approach showing the displacement. In this picture, you can see the scouring out of the approach fills behind the abutments. This aerial view taken shortly after the initial inspection shows the displacement clearly. In the downstream direction, you can see that the entire bridge, all 7 spans, although they were simply supported and not connected to each other besides dowels in the parapets, shifted as a unit. You can also see that in order for SANRAL to maintain connectivity on the N2, they had to use a southbound carriageway in a contraflow condition, meaning that one lane was dedicated for a northbound and one lane for the southbound, with temporary crossovers before and after the bridge. So from the evidence after the inspection, it became clear that the bridge had become buoyant when it was overtopped and pushed downstream under the hydraulic loads. The assembly of the bearings, shown in this picture here, have short locating pins. You can see it, these 3 red pins in the picture that protrude. These pins protrude 20 millimeters from the bottom plate into the top plate. Other than this, these short locating pins, there was no other connection between the superstructure and substructure that provided lateral restraint to hydrodynamic and debris loads. The bridge also had closure and facade walls on the piers and abutments. These did provide some lateral resistance, although they were unintended. These were purely for aesthetic purposes. However, on the morning of the inspection, as you can see in this picture here, all the closure walls and facade walls on the piers had broken off as a result of the movement, while the abutment closure walls, which is shown here, was critically damaged. Although these were critically damaged, they were still attached to the abutments. And it is believed that the deck wedged itself against these abutment closure walls. And it is believed that this is what prevented the bridge from being completely washed off the supports and into the river. Therefore, for the bridge to move horizontally, a combination of hydrostatic vertical uplift or buoyancy forces together with lateral hydrodynamic forces was required to unseat the superstructure of these pins and carry it down in a downstream direction. And this theory was tested with some calculations, which I'll show in a few slides later. Now looking at the hydrology and hydraulic analysis. So this analysis showed that the bridge was originally adequately sized to pass a 100-year flood event with at least 1 meter of freeboard and a 200-year flood event without overtopping. However, the evidence did show that the bridge was overtopped by 0.6 meters or 600 millimeters. So calculating the return period of the rainfall event from measurements showed that the rainfall event was estimated to be between a 100 and 200-year event. However, a 100 or 200-year event was not enough alone to overtop the bridge. What was observed in the morning of the first inspection was significant debris blockage at the bridge. So, through back calculation, we found that the combination of a 75% blockage and a flood size of 883 cubic meters per second, which equates to approximately 168-year return period, was the most likely combination to have resulted in the bridge being overtopped by 600 millimeters. We then undertook a sensitivity analysis because, of course, 75% blockage is quite a large number. But this sensitivity analysis showed that if you had to use less debris, it would then require a greater flood size to overtop the bridge by 600 millimeters. The flood size that would overtop it with at least 70 or 65% blockage would have been in excess of 1,000 cubic meters per second, which is unlikely. 1,000 cubic meters per second is now approaching the regional maximum flood territory. It is not unreasonable that 75% blockage could have occurred when one considers that the river reach is, although it is wide, but is relatively shallow, with the average height of the piers being only 3.75 meters above the river level. We were also fortunate enough to have found this video online. This is of the Mhlali River Bridge on the evening of the event. This video is taken from somebody that's positioned on the southbound carriageway, looking north. So he's sitting on the southbound carriageway, facing north. In the background is the northbound carriageway, and I'll just play this video for you. What you can see from the video is that the bridge had, or by the time the video was being taken, that the bridge had already been displaced. You can also see the water and debris streaming through the openings in the parapets. And you can also notice that the southbound bridge was unaffected. So this was a very telling evidence of what had occurred on that evening and provided great insight into our analysis. Okay, so then we tested the hypotheses on whether there was any hydrostatic uplift or buoyancy forces that caused the bridge to shift downstream. So hydrostatic uplift is the combination of buoyancy due to submersion in water and the effect of trapped air below or between structural elements. Now, the type of deck is important in this case study. Because it is precast beams with a deck slab which does permit the or does lead to air being trapped when the deck is submerged. We undertook this calculation. So just to go through quickly, buoyancy is the buoyant force is calculated by the density of fluid times the volume of fluid displaced. The volume of fluid displaced would be the deck area or the deck volume submerged plus the volume of trapped air between the beams. So looking at these numbers, the total concrete area submerged up to 600 millimeters high from the parapet was approximately 5 meters squared. Now, just bear in mind, this is meters squared per meter, so that's a volume. All the calculations here are per meter. And the area of or the volume of trapped air is 1.59 square meters in each of these bays between the precast beams, 1.59 meters squared per meter, and there's 6 of these, so that equates to 9.5 meters squared per meter. So the buoyancy force here would be the volume of fluid, which is approximately 10, multiplied by the volume of fluid displaced, which is the area of deck submerged, plus the area of air trapped between the beams, and that equates to 145 kilonewtons per meter of uplift force. And the self-weight of the deck, just taking the unit weight of the deck on its own, that equates to 132 kilonewtons per meter of downward force. So what this calc shows, although it's an approximation and the results are close, it does show that there potentially could have been enough of an uplift force to have lifted the bridge off the bearing pins unseat the bridge and shift it downstream, as was observed. So now, how then do we design and repair this bridge and improve its resilience to extreme weather events for the future? So these are just some general thoughts, but of course, the most obvious one would be to increase its hydraulic capacity. This could entail raising the superstructure, so building it at a higher level, or making it longer, increasing its overall length. While these are easy to implement for new structures, how do you do this for existing structures? Also, how practical or cost-effective is this? Typically, in this example, raising a bridge has, you would need to raise the approach roads, and that has significantly larger costs than raising the bridge on its own. So the problem we faced there was, how do we address this for the existing structure? We then had to look at alternative, and simple mitigation measures to, of course, reduce the vulnerability of bridges, to increase the bridge's resilience, and measures that could be retrofitted or adapted to this existing bridge. These are just general pictures not related to Mhlali Bridge, but these are just general pictures of other bridge damages from the same flood event on April 2022. So for the Mhlali River Bridge, to reduce the effects of buoyancy, small breather holes were drilled into the webs of the longitudinal beams to allow trapped air to escape. As was observed, the failure of the bridge was caused by the unseating of the bridge deck due to the combined effects of buoyancy and lateral hydrodynamic loads. If this trapped air was allowed to escape, the volume of water displaced by the submergence of the concrete deck alone, without the trapped air, would not have been enough to overcome the self-weight of the deck, and therefore the deck would not have been unseated. Another method to resist the unseating of the deck and to would have been to tie the deck superstructure to the substructure using a structural connection, or making the superstructure and substructure monolithic. This is typical of integral bridges. While this is easy to accomplish for new bridges, it's not so easy for existing bridges, and not all designs lend itself to integral bridges. And in this instance, the articulation of the bridge needs to be carefully considered before one links the superstructure or ties the superstructure monolithically to the substructure. So another method that we then used to increase the bridge's resilience was to increase its resistance to displacement from lateral hydrodynamic forces using a concrete restraint block, as we can see here. This was cast on top of the pier head, and on the abutment bearing shelves between the beams. So what this would do is, in the event of a lateral load, this would prevent the beams from moving laterally or horizontally in a downstream direction. These simple adaptations were considered sufficient to increase the bridge's resilience for what the bridge experienced on April 2022 and for future extreme weather events. Just other general mitigation measures to extreme weather events. It cannot be overstated the importance of regular maintenance of the waterway. As we observed in this instance, debris played a big role in the damage of the Mhlali River Bridge. In the absence of debris, the calculations show that the bridge would not have been overtopped and unseated. What is happening in eThekwini generally across all our river reaches is the proliferation of alien vegetation with a shallow root system, and the increase in the volume of litter being dumped in the rivers. This has meant that the frequency of blockages from debris has increased. So eThekwini has started to implement measures to, first of all, clean the river reaches, and secondly, implement a system to trap debris before it passes through the hydraulic openings. They have come up with a system called debris walls, which is, you can see it in these images here. These are constructed upstream of the structure, and trap the debris before it blocks the hydraulic opening, thereby allowing the water to pass through and not allowing the debris to block the hydraulic opening. Other general mitigation measures to extreme events is of course, it cannot be understated that all river bridges must be founded on rock, either spread footings on rock or end-bearing piles. In these two images here on the right, this was the Tongaat River Bridge, which the central pier had settled. This bridge was constructed in the 60s, and typically bridges of those ages were constructed on caissons. And it is believed that caisson did not necessarily go down to bedrock. And as a result of the floods in April 2022, the central pier had settled, thereby closing the bridge for a significant amount of time before this could be reinstated. And then, of course, to prevent scour of the approach embankments and scour around your foundations, scour protection around the supports and approaches is very important. Now, just looking at then the actual rehabilitation of the bridge. So what needed to happen was the bridge superstructure needed to be jacked vertically, as well as horizontally back into position, one span at a time. It is quite astonishing to believe that the entire superstructure moved in a matter of seconds as a unit downstream, but it took us months to reinstate it. Approximately 3 months was the contract period. And each span had to be done individually to reinstate it back into its original position. It just goes to show the power of nature. This project then required specialized temporary works designs for the custom-made steel brackets fixed to the substructure to support the jacks and the sliding beams. In these pictures here, you can see these custom-made brackets fixed to the piers. This is supporting the jacks, which jacked up the sliding beam, which the bridge was sitting on, and then we had horizontal jacks pushed off another bracket, which then pushed the bridge back into its position. Before we reseated the bridge back into its new position, we replaced all the bearings, and once the deck was reseated in its position on new bearings, we replaced the asphaltic plug joints. And then, of course, both approaches were reconstructed, and extensive gabion and scour protection was installed to prevent, hopefully, future scouring out of the approach embankments. So in conclusion, what we can say is that an extreme weather event exceeding a 100-year return period, together with significant debris blockage, overtopped the Mhlali River Bridge. This resulted in hydrostatic uplift and lateral hydrodynamic forces, which unseated the bridge superstructure and shifted it downstream by 600 millimeters. The bridge was subsequently rehabilitated, and its resilience to future extreme events was improved by installation of simple measures such as the breather holes, which allow the trapped air to escape, as well as the restraint blocks, which increase its lateral resistance to horizontal hydraulic forces. We're also proud that this project also took home the SAICE Technical Excellence Awards for structural projects, and that was in 2024. This is just some pictures of the completed structure. This is looking at the bridge in a northerly direction, and this picture is looking at it in looking south. And then just to finish off, just some acknowledgements. So of course, Sandral was the client for this project. We were the consultants. DT Mlangeni was the contractor, and they utilized the services of MMP Construction as specialized structural contractors who undertook all of the jacking operations. That concludes my presentation, and I'll now hand over to Thobekile. Thank you very much for your attention.
Thank you so much, Mohammed. Very good evening, everyone. My name is Thobekile Ngobo, and I will be presenting on the fire damage assessment and repair of the Sonye Road Bridge. Can everybody see my screen?
Yeah,
Yes,
it's
we can.
visible.
All right, perfect. Let us begin. So just before we start, I would like to give us a quick presentation outline of what we'll be speaking about today. I will begin with giving an introduction. I will then move over to our project location, talk about the structured details, post-fire assessment of concrete, where we will look at the visual inspection, the fire impact on the concrete color. We'll then look at the concrete core analysis. We'll move over to the sustainable response, the technology as a driver of sustainability. There we will look at digital twinning, thermal imagery, and microstructural analysis. We'll then head over to our sustainable repair and protection, and lastly, we'll end off with a conclusion. So one of the critical issues that affect our infrastructure is fire. And with the increasing development of ground transportation networks, the transportation of flammable materials such as petrol, diesel, and other hydrocarbons, bridge fires have gained massive prominence over the years. In an analysis of 154 incidents that occurred between the years 1997 and 2015, it highlighted that tankers transporting flammable fuels are the main cause for bridge fires, such as in the case of B112 Sanya Road Bridge. On the right is the actual footage taken on the night of the accident. The project that we'll be talking about today is located in Durban, KwaZulu-Natal, on the national route N2, section 25 at kilometer 11.4. This is a strategically important section of the N2 corridor, which serves as a major national highway. And because of this, the structure plays a vital role not only in local connectivity, but also in the national transport economy. The bridge is a rigid frame structure with inclined columns. The deck is a post-tension concrete box girder with depths varying between 1.8 meters and 1.2 meters. On the 4th of August of 2015, the collision of a petrol and diesel tanker led to the damage of this bridge. The two tankers on the northbound carriageway and their fuel content subsequently burst into flames, and in the ensuing fire, extensive damage was done to the road, pavement on the N2, and to portions of the bridge. This Class B fire reached alarming heights, leading to visible damage such as concrete spalling, cracking, and delamination of the soffit and the piers of the bridge, especially on the main span. And although the damage was concentrated on a specific section, the overall durability implications were quite severe. And that's what prompted our detailed assessment and sustainable repair strategy that I will discuss next. Traditionally, fire damage structures are assessed through methods such as visual inspection, color observation, and core sampling. These approaches can provide valuable insights into the extent and nature of damage. However, they also have certain limitations. Visual assessments can be subjective, relying heavily on experience, while core sampling, on the other hand, and other destructive test methods are selective, are time-consuming, localized, and can cause additional damage to the structure. In this project, we then used these methods selectively and strategically, extracting only a small number of cores, for example, from representative areas to confirm our observations, rather than relying on them exclusively. So this balanced approach ensured that destructive testing served its most important role, which is verification. It allowed us to confirm the data obtained from non-destructive techniques without unnecessary material loss. And in doing so, we were able to maintain accuracy while still aligning with our broader goal of sustainable and minimal invasive assessment. So, while these methods continue to serve us, they don't always give us a full or accurate picture, especially for this large structure. And that's where our focus on advanced, data-driven, and sustainable assessment methods comes in. So fire-induced spalling is a phenomenon that occurs when concrete is exposed to very high temperatures, typically above 300 degrees Celsius. And during the fire, moisture trapped within the concrete turns rapidly into steam, creating internal pore pressure. And on the structure, surface spalling was observed on the soffit and the sides of the box girder, exposing the reinforcement in several areas as seen in the image displayed. The exposed reinforcement definitely indicates a loss of concrete cover, which is critical for protecting the steel from corrosion. And from a sustainability standpoint, understanding the extent of spalling is vital because it allows us to target our repairs only where the concrete has lost structural or protective function, rather than replacing large undamaged sections unnecessarily. The fire itself doesn't only affect the physical structure of concrete, it will also alter its color and appearance, providing visual clues about the temperature exposure during the event. Concrete containing quartz-based aggregates often will exhibit a pink to reddish discoloration when subjected to temperatures between 300 degrees Celsius and 600 degrees Celsius. And in our inspection, areas of pinkish discoloration were observed near the fire's location on the soffit and the pier faces. However, relying solely on color as a diagnostic tool presented quite a bit of a challenge, because the natural color of the quartz aggregate used in concrete already had a light reddish tint, making it quite difficult to distinguish between heat-induced discoloration and natural variation. And as a result, the color observation was only used as a preliminary indicator, supported later by core sampling and doing a lab analysis. Concrete cores were then extracted from the soffit of the bridge at several locations. The images shown here illustrate the contrast in condition across the structure. The core on the right, taken directly above the northbound carriageway where the tanker fire occurred, showed significant surface cracking and spalling, indicating exposure to intense heat. In comparison to the core on the left, taken from the northern edge of the bridge away from the fire's epicenter, showing no cracking or discoloration, confirming that the heat effects were highly localized. The compressive strength tests shown on the far right revealed a slight reduction in strength at the depth of 35 millimeters of the fire damaged zones, but the strength beyond that depth remained well above the original design requirement. And so, having understood how assessments have traditionally been done, the question then became, how can we assess and repair in a way that's smarter, faster, and more sustainable? And that's where our approach focused on precision through technology. Our sustainability philosophy was guided by three principles: accurate assessment, targeted repairs, and sustainable methods. This is where technology plays a transformative role with the use of digital twinning, thermal imagery, and the use of microstructural analyses. So the first key tool we used was digital twinning, essentially creating a 3D digital replica of the bridge. Using UAV, or also known as drone-based surveys, we captured thousands of high-resolution images across the entire bridge deck and piers. And then these were processed to generate a 3D model that reflected the bridge's actual condition. So this was more than a visual model. It became a data-driven map of the structure. We could overlay the locations of the cracks, the delamination zones, the exposed rebar, as well as the fire damage. The result was that we could see the damage distribution quite clearly, not just at isolated points where we took samples, but across the entire geometry of the bridge. And this had a massive sustainability impact. By identifying exactly which areas were compromised, we avoided, once again, unnecessary demolition. We focused repairs only where it was required. That meant less material wastage, less energy use, and a lower carbon footprint. It also meant faster repair timelines, which reduced traffic disruptions and the indirect environmental impacts of prolonged construction. The next technology we utilized was thermal imagery, and this played a key role in identifying the hidden damage. So after a fire, the concrete can appear fine on the surface, but internally it may have delaminated, meaning concrete has separated due to heat and stress. So these cavities are hard to see, but they behave differently under heat. They cool and heat faster than the solid surrounding concrete. So we used then thermal cameras to scan the surface and detect those heat differences, as you can see on the screen at one of the piers. This allowed us to map out delamination zones correctly. And that's what's powerful here, is that the process is non-destructive, it is fast, and it is quantitative as well. We didn't necessarily need to core about 20 or 30 samples, we could instead just core at the critical zones. That not only saved time, but it reduced waste from unnecessary core and patching. A microstructural analysis was then carried out to further establish the depth and severity of fire damage to the concrete. This analysis involved examining concrete samples extracted from the soffit of the bridge. The findings revealed that fire-damaged area experienced the most significant thermal exposure, with damage extending to a depth of approximately 30 millimeters. And under microscopic examination, the concrete matrix showed clear signs of thermal decomposition, including a dehydration of yttringite, which typically dehydrates at a temperature of 80 degrees Celsius and 150 degrees Celsius, as well as a decomposition of calcium hydroxide, which dehydrates at a temperature of above 300 degrees Celsius. However, the quartz particles in the samples did not undergo any phase transition, which normally occurs at around 570 degrees Celsius. This suggested to us that the structure had been exposed to temperatures below 500 degrees Celsius. So that meant the fire was high enough to cause surface damage, but not severe enough to compromise the internal structural integrity of the concrete. The elemental mapping shown on the screen compares the fire-exposed concrete to unaffected concrete. And in the unaffected sample, calcium, for example, is clearly present and evenly distributed. Whereas in the fire-exposed sample, there is a noticeable reduction in calcium concentration within 30 millimeters. This reduction corresponds with the loss of calcium hydroxide and indicated a potential decrease in the strength as well as the durability in the surface zone. So based on these findings, the recommendation was to prepare and remove the existing substrate to a depth of at least 35 millimeters in the fire damage zones. So once the assessment confirmed the extent and depth of the fire, the repair strategy was then guided by the European Standards EN 1504, parts 1 to 10, which provides comprehensive principles for concrete protection and repair. Each repair measure was carefully selected to achieve two parallel objectives: durability and sustainability, ensuring that the bridge's service life was extended while minimizing material use, carbon emissions, and maintenance needs. The first measure, concrete restoration, involved reinstating the damaged concrete cover using low carbon repair mortars. This provided protection for the reinforcement while at the same time reducing the need for future large-scale interventions, effectively lowering the project's long-term carbon footprint. Next, restoring passivity and control of anodic areas address the corrosion potential of the reinforcement by increasing cover, coating the reinforcement with a zinc-rich primer, and applying migrating corrosion inhibitors. The repair decreased further steel corrosion and extended the lifespan of the existing rebar. Protection against ingress focused on preventing the re-entry of water and chlorides through surface impregnation, crack sealing, and coating system. Finally, moisture control was implemented using a hydrophobic impregnation. So together, these measures demonstrate that durability and sustainability are not necessarily separate goals, but they are mutual. By protecting existing materials, extending service life, and reducing the frequency and scale of future repairs, the overall environmental impact of the bridge throughout its life cycle is significantly reduced. In conclusion, sustainable repair begins with accurate data-driven assessment. Technology reduces uncertainty, waste, as well as carbon impact. Targeted interventions preserve existing materials and extend the service life. Durability and sustainability work hand in hand. And lastly, smarter assessments today mean fewer repairs tomorrow. Thank you so much for listening.
Thank you, Tobekile. Thank you. So, good evening, Sani Bunani, Mpolweni, and Namaste, how's it? So I'll be your entertainment for this evening, as Tom said. So someone has their hand up. Okay, I think we'll take questions after the presentation. Okay, so I'm just kidding. I have a presentation. Don't. There's no entertainment. Apologies. Let me get my presentation up.
You're
Okay.
good to go, Abish.
Thanks, Tom. Okay, so I'll be presenting on the emergency rehabilitation of the Mzimkhulu River Bridge. So let's go for it. So yeah, just a brief introduction. Out here. So the Mzimkhulu River Bridge, located within the Rain Konyani municipality, within Port Shepstone, which is south of Durban, within the Mzimkhulu River estuary. Visible rotations to the pier negated an emergency investigation that was undertaken by Naidu Consulting, and as part of the mandate, we were in charge of designing repairs to Pier 2, as well as reinstating the durability to maintain the bridge's serviceability. Okay, so just a bit on the structural form, the bridge was built in the 1950s, and what you are seeing here is a Revit model that was developed by our BIM lead. Let's move on. In terms of the structural form with respect to the spans, it comprises of 15 25-meter long simply supported spans, contributing to a total of 375-meter bridge length. Now, one may ask, 25-meter spans, is this post-tension? The answer is no. In the 1950s, this was not so unheard of at that point in time. So yeah, so no post-tensioning. Okay. In terms of the bridge form, in terms of the cross-section, the deck comprises of a cast in situ reinforced concrete T-beam cross-section, and there exists a longitudinal joint that separates the roadway corridor on the left and the railway corridor on the right. The superstructure is supported on wall-type piers and abutments, and the deck and the overall substructure is supported on a foundation that comprises of 4.2 diameter caissons. So to take you through the bridge damage that occurred, so after the Pier 2, which is numbered from the Port Shepstone side up north, after the Pier 2 settlement, the Department of Transport contacted Naidu Consulting to undertake a detailed investigation, and as part of the scope of work was to remediate Pier 2 as well as to reinstate durability to last a minimum of 25 years, which is the remaining lifespan within the life cycle of the bridge. And lastly, since there's an issue on Pier 2 specifically, there's a foundation issue. DOT has then also asked us to investigate other piers to ensure that whilst we are in construction, we mitigate against any further reoccurring concerns. Okay, so just an important note. So this is looking at the bridge in elevation with Port Shepstone on our left and Hebridean on our right towards Durban. And also, if I bring up the Google Earth image at the bottom, you will notice the river flow is more in a downwards direction. That's the flow of the Mzimkhulu River. However, we do have the oceanic current also presenting a tidal action, which creates a turbulent flow within these piers. Also important to note that where the red outline is, it's actually a river train retaining wall that connects to Pier 1. Now, what this does is essentially it then redirects the river flow, which then presents predominant flows through spans 2, 3, and 4. Then moving on in terms of the Pier 2, in terms of Pier 2 and what had occurred at that location, looking at the bridge in an elevation photo, you can see that the pier rotated towards the downstream, which caused the pier, settled on the downstream end, which caused a rotation as well as a translation relative to the deck, to the superstructure. And this was also noted at the top bearing seat. It was evident that there was a approximately 500 mils movement. So in addition to this movement, this movement resulted in secondary effects, which can be seen in this photo where the edge beam support actually sheared off. In addition, the opposite edge beam lifted off the pier. Now, following all of these movements, redistribution of forces occurred, and as a result, shear cracks developed along the transverse diaphragm, and this was noted and recorded as well. Okay, for added visuals, this, ladies and gentlemen, is a digital twin model comprising of a Revit model overlaid with a point cloud scan. So the gray depicts the actual Revit model in the original design location, and the rendered view is the point cloud scan, where you can actually clearly get a feel for the movement and start to be understanding as to the criticalness of the specific Pier 2 structure. Okay, in terms of general durability, the superstructure has exhibited excessive sprawl because of the high chloride exposure. This is potentially due to its location next to the ocean. Secondly, the safety handrail systems did not actually comply with the current standards. Hence, and therefore, the current, and also in addition to that, the condition of the handrails do not make them fit for its purpose. This same handrail system was also utilized on the roadway corridor side to provide containment for vehicles between the roadway corridor and the river. This is hazardous and is not compliant from an impact load perspective. Now taking you through to the rehabilitation works. So with regards to the pier, specifically to the Pier 2 rehabilitation, so time constraints and risk of further settlement, considering those parameters, the design and tender documentation were required rather urgently. Hence, the settlement investigation was investigated during construction. So now I'll take you through two of the design considerations along with that, some of the design constraints. Of the two, so three was considered. One we had discarded at the early stage, which was to demolish the entire bridge and replace with a incremental launch method structure. This, however, was not considered and taken to the next phase due to its unfavorable cost. Moving over to the option one that was envisaged, this was to demolish and reconstruct. So focusing on Pier 2 specifically and the adjacent spans, which is 2 and 3, we then deconstruct or demolish the superstructure as well as the pier. Thereafter, construct piles and associated pile caps, along with reconstructing the pier and reconstructing the superstructure. Now, this in itself is a safe design. However, and also it mitigates the risks of further settlement and disastrous concerns during construction. However, there is an environmental impact and cost implication to this. Moving over to option 2, which was the preferred option, we start off with installing a safety support bracket. This supports the edge beam, which combats the reduction of the pier support from the previous images illustrated. In addition, now that we have the superstructure, maintaining that in position, the distance from the riverbed level to the soffit of the superstructure was was sub-minimum to the actual height of a piling rig. So we could not get piles. It's difficult to get piles under the superstructure. In this case, we now installed larger 1350 diameter piles, which are located adjacent transversely to the pier. Then we construct the pile cap, which is shear connected to the existing caisson cap. Thereafter, we jack the bridge and position it in its original position, replace the bearings on new plinths, and lastly, we reinstate the plumbness of the pier to make it aesthetically pleasing in relation to the other piers. Now, the benefits of this specific design is it maintains the existing spans and pier, which results in reduction of cost and environmental impact, which we'll touch on further later. In terms of the design drawings, so this is the typical repair rehabilitation detail for Pier 2, which comprises of an extension of the caisson cap, and as you can see, it's shear connected to the existing caisson cap. There you have on either side, that's the thickening that allows for the plumbness retrofitment, as well as we have to demolish the closure walls and gain access to the bearings to replace them over with plinths. And on the right hand side, we have the jacking towers, which is utilized to jack the bridge in position. Additional details were provided. This was actually provided by the contractor. It's a temporary works design, which is the temporary safety bracket that was installed initially. So this temporary bracket is shear connected to the pier itself and has a short cantilever that supports the edge beam. This also includes on site a gauge and back mark so as to determine if any further movement is recorded on site. This will gauge in terms of safety as well as inform the design engineers and geotechnical engineers to assess further. On our right hand side, we've got the extension of the pier. That's to reinstate the plumbness. In terms of the option 2 and what benefit it has from a sustainability perspective, and also for you to get a feel of the saving in terms of CO2 equivalent emissions, here's a quick calc. And not to mention, notwithstanding, Mr. Adrian Pillay, would like to thank him for his efforts in this and extensive research he had undertaken with regards to CO2 equivalent emissions. So similar approach to Kaneland's presentation, a 240 CO2 equivalent per meter cube factor was utilized in this calculation, and the respective concrete volumes that was utilized was the deck and pier, as per option 1 that was to be demolished, and adding those two up and converting that to a CO2 equivalent emission value, we end up with 317 tons. Now, to put this into perspective, we have this excellent comparable study where it is 317 tons is equivalent to 1,300,000 kilometers driving a normal petrol vehicle for that distance, planting 5,200 trees. This is over the course of 10 years, as well as powering 41 homes for a year. Taking 320 one-way trips from Johannesburg to London, and lastly, the burning of 12,000 liters of petroleum. Okay, from a durability perspective, repairs perspective, we envisage the use of sacrificial anodes. So, corrosion. Let's talk about corrosion. So, in terms of corrosion occurs predominantly when metal atoms lose electrons and become ions. So that's the first formula on the top there. And this corroded metal, in this instance, we're calling this the anode. Corrosion in itself is accelerated in a chloride contaminated reinforcement concrete type environment. Now, this concrete system itself acts as a galvanic cell, which is essentially a migration of ions, right, which initiates that. So Therefore, that migration of ions can lead to the breakdown of the anode, which in our case is our reinforcement steel. Now, ways to mitigate this, like one may ask, how can we reduce this effect? Well, the answer is cathodic protection, but specifically in the form of sacrificial anodes, right? Now, once we introduce a sacrificial anode, what is a sacrificial anode in the first place? So, sacrificial anode comprises of a highly reactive metal such as zinc, magnesium, or aluminium. And now essentially what this does is it reverses the role of the anode and the cathode. And in that being said, the reinforcement steel now becoming the cathode is more resilient and thus breaking down the anode, which is now our sacrificial metal. So in this instance, we are protecting our steel and promoting a much durable structure. So this approach was specified for all spoil repairs in the bridge, specifically due to the location of the bridge being at the ocean. This served as best practice to reinstate the durability of the structure. Additionally, to protect the concrete surface, a hydrophobic impregnation and saline additive was used to create a barrier against water and chloride ingress. This was also mentioned to Vakili as well. And lastly, we performed a project evaluation on the Mzimkhulu River Bridge. This is utilized to guide us as Naidu Consulting to determine shortfalls and to better improve our response on these types of projects. Okay, so some of it to start off with is the safety risk aspect. So based on the defects and potential movement, the bridge was closed to public vehicular traffic. Now, during construction, the safety of workers under the bridge was also a concern. Hence, as discussed previously, a temporary bracket was installed. In terms of social implications, the P3 of 1, commonly known as the R102 route, is essential for business within the Ray Nkoniani municipality. So the road closure actually imposed a huge economic strain on local communities. In terms of environmental implications, the alternate route at peak hours has seen slow-moving traffic for longer than usual periods. This generally would result in higher carbon equivalent emissions. While diverting the river in accordance to the Environmental Management Program, it is essential to protect the estuary ecosystem. Therefore, the depth of the new channel leading to the ocean must be continuously monitored to ensure consistent flow depth. And lastly, in terms of the cost implications, due to road closure, an alternate route was required. The cost, however, of the traffic accommodation and associated road maintenance could have been averted if the road was not fully closed. So of all impacts mentioned and the evaluation undertaken, the most critical one was the full road closure. When we examined how engineers can better mitigate safety risks without full road closure in a manner that assured our bridges remain safe, the answer to this resulted in bridge instrumentation, specifically the use of early warning detection systems. So we have movement sensors, also known as tilt sensors. What are these? Essentially, these measure small changes in the angle or movement of the attached bridge element. They help detect early signs of settlement and rotation and provide real-time alerts as frequent as every minute. They also are available wirelessly, with some capable of over 10 years maintenance-free monitoring. In terms of river level sensors, they monitor the water depth and flow beneath the river in real time. This warns us of possible flooding or scour around the bridge piers. This system together enables engineers, specifically to this project, to monitor the rate of pier rotation and pinpoint the exact date and time of any excessive movement. Such data can be correlated with flood events or other external factors, providing critical insight for structural design and geotechnical investigations. In turn, these sensors could have averted the need for full road closure. In conclusion, given the environmental and social circumstances globally and locally, As engineers, we need to ensure our designs incorporate sustainable practices. In this instance, by maintaining the existing infrastructure, we reduce cost and carbon emissions. We also need to promote resilient infrastructure. In the case of the Mzimkhulu River Bridge, through the adoption of durable repair methods and bridge instrumentation, structures can effectively adapt and maintain serviceability for the remaining service life. With that, ladies and gentlemen, I'd like to say thank you for availing this time this evening to listen to our presentations, and I hope this information provided was resourceful and enlightening. Thank you. I think I now would hand you over to Mr. McEwen.
Thank you, Naidu Consulting team, for very, very informative. Although I'm a putt marker, not a bridges guy, even I found the stuff very interesting and informative. There are some questions in the chat. I will just read them out one at a time and allow the appropriate member of the team to respond. The first is from Lloyd. It refers to the pedestrian and pipe bridge, which I think was project 1. Considering that the rail bridge had deteriorated beyond rehabilitation, what was the condition of the substructure, and how did you integrate the differing design lives of the superstructure and substructure in the design?
Hi, Tom. Thank you. Hi, Lloyd, for your question. Adrian here. The substructure was in good condition. However, at the design stages, the cores were extracted to determine the strength and durability properties of the in-situ concrete. These were found to be within tolerances. Notwithstanding those tests, the existing designs catered for a railway live load, which was greatly reduced to now a mere pedestrian and pipe services load. I hope this answers your question, Lloyd.
Yes,
Sure.
it does. Thank you so much.
There we go.
Okay,
and then Tobakile, there's another question from Lloyd for you. On the Sanya Road Bridge, what was the original concrete cover of the bridge? And did the fire have any effect on the reinforcing steel itself? If so, how was the moment capacity of the bridge assessed after the fire?
Good question, Lloyd. So I'll answer it in 2 parts because I think you have 2 questions there. So the original cover, as per the as-built, was 40 millimeters. However, we did observe on site that other areas had low cover, obviously due to the construction deviations. Second part of your question, the fire didn't have a significant effect on the steel itself. Firstly, none of the steel lost its cross-sectional area. And as well as the fact that it is a post-tensioned bridge, none of the cables were affected by the fire as well. And if you recall, I did mention that in the microstructure, the quartz was still present in the concrete matrix, suggesting that the temperatures were below 500 degrees Celsius. And steel will typically lose significant strength at around or above 600 degrees Celsius. So I hope I answered your question.
Yes, thank you so much.
Okay, then there's another question for you, Adrian. This one refers to, again, the pedestrian bridge. How did you deal with the expansion of the HDPE pipe that was encased in concrete? I'm assuming different expansion factors.
Yes, Tom and Gofi. So the HDPE pipe was fully encased in concrete. Hence, it prevented the movement of the pipe, and the subsequent stresses from this restraint was accommodated for in the designs of the deck. Notwithstanding that the pipes were free at the bridge abutments at the ends of the decks, of the deck rather.
All right, thank you, Adrian. And then the Mzimkhulu River Bridge, was there a difference in the damage between the beams supporting the roads and the ones supporting the rail?
Hi, Tom. Good man. Thanks for that question. So in a nutshell, the main girders, the answer is no. So there weren't any difference in terms of of damages to the main girders, the longitudinal members. However, the main structural element that was actually in that line of distress would be the transverse diaphragm beam, and that incurred shear cracks more towards the inland side, where you've noticed, as per my images, the edge beam had the edge support sheared off. From that location onwards, because of the concentrated forces, as the entire deck rotated, and it was concentrated towards the edge of the pier. That's where there's a point load acting upon the deck. Hence, the diaphragm transverse beam surpassed its initial design shear capacity, and that was what has led to those shear cracks. But in terms of the main girders, no.
Okay, then there's a
Thanks,
question from Isaac in Gwenya, and just out of interest, he wants to know, did you have to have an EIA, or were there any triggers for NEMA on these rehabilitation works that you've presented on?
Okay, so out of interest, yeah, so this was an emergency rehabilitation project. It underwent a special Section 31A application, and that negates some certain timelines. However, if a full EIA process was undertaken, and in terms of the triggers, the major one would be we are working in an estuary. So an estuarine specialist was appointed, as well as in addition to that, a heritage specialist was also appointed because the bridge is over 60 years old. So those were the triggers, yeah.
And then Masanda Dudula has a tongue-in-cheek comment or observation. First of all, thank you very much, the NADU team, for the interesting presentations. And then the question is, did you not consider leaving the edge beams plumb repairs, where you added that like sort of tapering strip to it, if they didn't affect any structural integrity of the bridge for a new leaning bridge? So I don't know if he's looking for us to get Leaning Tower of Pisa tourist attraction on your bridge, which
Exactly.
you've now denied the opportunity.
So yeah, so Tommy, I think, yeah, as per DOT's project scope, you are right. The Leaning Tower was not present at that project scope. But in terms of reinstating it, look, the IMAFA entities have very strict protocols with their architects in terms of approving bridge aesthetics. And when it comes to these sort of retrofitments, it's always necessary to include in your design to reinstate to the existing and maintain certain aesthetics, so as to not cross another hurdle down the line. So yeah, that's it.
Right, I think that's a wrap. I see Josh, would you like to, as the Makulu Numzan at NADU Consulting, certainly in the structural environment, any comments that you'd like to add for your team?
No, I think just well done to the guys. Very informative presentation, and the questions that have come through as well. It's so good to see such an active presence on this platform, and the number of people that have attended. And well done to SAICE, and thank you, Tom, to SAICE and yourself for the opportunity for the youngsters in our organization to have such a platform to showcase the experience and the projects that they are currently busy with. So thank you once again, Tom.